Hello, this is the next video in a playlist that I'm calling probability measure, and here we're going to look at extending a probability measure on a field that can be extended to the probability measure on a sigma field, specifically the minimum sigma field generated by the field F. Now this is a follow-up video to two other videos, background video 1, where we looked at the extension of a probability measure from a field to a slightly larger class of sets, and then BV2, background video 2, it's the extension of that probability measure to all subsets of omega. And it turned out that that extension to all subsets, then we lost the property of a probability measure. So in this video we're going to knock back the sets from all subsets to something smaller where we retain that probability measure aspect. Now, as a reminder, in BV2, all sets A, a subset of omega, this was the measure. It's the mu star of A was the infimum of all sets that cover A and that they live in G. Now G was a slight extension from the field, so it included the countable unions and countable intersections of sets. Mu and G are defined in BV1. We're also going to make use of BV3, which is the continuity of a set function, in the proof that we're going to do here. So here's the theorem. Under BV2, let's let script H equal this. So it's all sets in omega such that mu star H plus mu star H complement equals 1. Now when we allowed it to be any set in omega, this the sum of these two measures was greater than or equal to 1. So we're getting rid of the sets where this measures more than 1. We're going to show that script G is a subset of script H, and script G is defined in BV1. We're also going to show that script H is a sigma field, and mu star is a probability measure on script H. So let's just jump in. So by BV2 lemma 3a, mu star is equal to mu while we're on sets in G. Now since the empty set and omega live in G, that says that mu of the empty set plus mu of omega equals 1. Okay, and so since these live in G, that tells us that mu, right? So the complement of each is 1, so that tells us they also live in H. But since the mu's agree, mu agrees with mu star, that says that this also has to equal 1. Now let's let A be any set in G, script G, and we showed that mu of A is between, it's a probability measure, so it's between 0 and 1. We know that omega is equal to A union A complement. Mu star omega is equal to mu omega, right? But that's equal to mu A plus mu A complement, right? Because those are disjoint sets. It's a finite union that makes up omega. But these agree on sets in G. So this says that mu star A plus mu star A complement is equal to 1. So hence A is in a script. Right? So all sets in G live in H. So we've just shown that G is a subset of H. Now we need to show that H is a sigma field. Now and there's 3 steps. We'll do it in 4 though. From part A, we know that the empty set and omega live in script H, right? We just showed that. So that means H is non-empty. So that's the first part. Now we need to show that it's closed under complementation or complements. So, but by definition of H script, H is closed under complementation, right? Just the way that it's defined. If H is in here, H C has to be in here, right? Because the measures equal 1. So it is closed under complements. Next, let's show that H is closed under finite unions, meaning, a field. So let's let H1 and H2 be any sets in omega. So that's the key step in this little part here. They're in, then by background video 2, lemma 3b, we know that this holds, that the measure of those two sets is greater than or equal to the measure of the union plus the measure of the intersection. And it was actually this property that made mu star fail as a probability measure, because this is always greater than or equal to 1. But for this theorem, this is true for any sets in omega. We're going to call this equation 1. Now, normally we would put, we could show H1 complement intersect H2 complement. We could put that right here, and then these two sets here, and then we'd get the same property. But since this equals this, we're going to put this notation here, right? So it's essentially the same, the previous equation, but we're using complements. But we're using this type of setup now. So that's true if we allow H1 and H2 to be any set in omega. But let's let H1 and H2 be sets in script H, right? So we're restricting it just a little bit. They live in H script. And let's add 1 and 2, equations 1 and 2, right? So we get this side is here, right? And then equation 1, that's this. And then over here we get this, and then equation 1 we get this. But the way H is defined, we know that mu star H1, mu star H1 complement, this is 1, has to be a requirement to be an H. And this is 1. So this is equal to 2, right? But by the background lemma, we know that the probability of a set and its complement is greater than or equal to 1. So the addition of this plus this is greater than or equal to 1. And we also know that this is greater than or equal to 1. Has to be. But if we know this is greater than or equal to 1, and we know this is greater than or equal to 1, but we know the whole thing equals 2, or it can't be more than 2, that forces each of these to be 1. Right? So that means this is 1. But this is saying that it's closed under finite unions, right? Finite unions are still in H because this equals 1, right? So it is a field. Now in step 4, we're going to show that mu is countably additive on H script, meaning it's a field. So when a measure is countably additive, it means that the field, or the sigma field, also it encompasses countable unions and countable intersections. All right, that's equivalent. We'll show that mu is continuous from below, and refer to the background video 3. If it's continuous from below or continuous from above, that means it's countably additive, which means it's a sigma field. Okay, and so that's sort of the game plan here. So let's let Hn be in script H, and this is for all n, right? So since Hn is in script H, we know its complement has to be in there. And we're going to choose the Hns so they increase to H. So H1 is a subset of H2, which is a subset of H3, and they have a limit to H. Now, by background video, lemma 3b, we know that this has to be greater than or equal to 1, right? Now, why is this? Well, we know that the Hns live in H, but we don't know that what they limit to lives in H, right? H and H complement are just sets in omega. We don't know if they live in H script. So this property holds, and we showed that in lemma 3b and BV2. Now, by lemma background video 2, lemma 3D, we showed that the limit of Hn, of mu star of Hn is equal to mu star of H. That we showed. But now we still don't know if H lives in H script or not. So let's let mu be greater than 0 and n large. Whatever, in quotes, large. So that means since this measure limits to this measure, it gets really close. So we can pick n large enough that if we add a small amount to this, it actually goes above this measure. That is by this property. Now we do know that Hn is a subset of H. That's the way we defined it, right? That means H complement is a subset of Hn complement. And if we look at mu star H complement, that has to be less than or equal to mu star Hn complement. And this is for all n. Now let's add these two equations, right? This plus that is less than or equal to these sets. And so this, we know since Hn and Hn complement live in H script, this adds to 1. That's the way H was defined. But epsilon is picked arbitrarily, so we can let it go to 0. So that means the addition of these two measures is less than or equal to 1. But we showed that it has to be greater than or equal to 1 too. Right? So that means that they have to equal 1. Well, if H and H complement equal 1, that means they live in H script. So that means mu star is continuous from below, and by background video 3 is countably additive, and that means it's closed under countable unions. And that means H script is a sigma field. Now the big theorem in this video is it's 4 lines. A probability measure on a sigma field F can be extended to a probability measure on sigma of F. And this means the minimum sigma field generated by F. Now, from previous videos, we know that the field F was a subset of script G, and this is a subset of script H. And we know H is a sigma field. So the minimum sigma field generated by F has to be a subset of script H. So if we restrict mu star to this minimum sigma field, then that's the desired extension. So mu star is a probability measure on the minimum field generated by F. And thus we've proved a theorem. Now, in the next few videos, we're going to work towards some requirements to make mu star a unique extension to this minimum sigma field. Right now it's not. And that's all I have for this video, so I hope you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks, bye.